Welcome back. Last lecture, I showed you the torsional and steric effect in molecules like ethane and propane. We said in an eclipse condition or eclipse conformation, when two hydrogens are facing to each other, the system will be unstable by 4 kilojoule. And if you replace one of the hydrogen by methyl, that's going to cause the system 4 kilojoule. And if you have two methyls are facing to each other, in this case, it will be 11 kilojoule unstable. By 11 kilojoule, it will be unstable. Okay, so and the first example that we went through it was ethane. Okay, so we have ethane, and that's C2H6 carbon attached to carbon. In each carbon, it has 3 hydrogen atoms. Okay, and we said in eclipse condition, we're going to have 3 pairs of hydrogen facing to each other, and because we have 3 of them, so we say 4 multiply 3 times, it will give us 12 kilojoule. And that was the reason that the barrier for an eclipse conformation of ethane, it will be around 12 kilojoule. Now, what will happen if I replace one of the H by methyl? If I replace H by methyl, energy from 4, it will go up to 6. Okay, so from 4, it will go up by 6. But I'm going to replace only one of them. Okay, only one of them. So one of this 4, it will be replaced by 6 kilojoule. And as you see here, and for a molecule like ethane, I have okay, 1. That's going to be 4 kilojoule, here 4 kilojoule, and this is going to be the new one, and it's going to cost us 6 kilojoule. So 6 kilojoule here, and therefore 4 kilojoule. And if I add these numbers, okay, 8 plus 6, it will be 14 kilojoule. And this is the reason the barrier for rotation over single bond of carbon-carbon and propane, it will be around 14 kilojoule. Okay, again, this one is going to cost you 6 kilojoule. Okay, next. What will happen if we replace another hydrogen atom? Let's say we're going to go after one of these hydrogen atom and replace it by methyl. And in that case, you will have technically 4 carbons. And that structure will be butane. Okay, butane. Okay. So if you start with butane, the most stable structure for butane, it will be the anti. Okay. So let's draw the most stable structure for butane. Okay. It will be this. You put CH3 here, and you have H. Now, the one on the back, you need to put it 180 degrees far from the first methyl group. Okay, and I get H here, H, and that's going to be CH3. Okay, this one, it has 2 substituent or 2 methyl group in 180 degrees far from each other. So we say theta. The dihedral angle is around 180 degrees. Okay, and the name for this structure is anti. So anti. The anti-conformation for butane is whenever the dihedral between 2 methyl groups is 180 degrees. Why 2 methyl groups? Because those are the bulkiest group. Okay. Now, what will happen if I change? Okay, if I change position of them. Okay, let's say we decide to change position of methyl. Okay, so I'm gonna go after one of the methyl. Let's say this methyl. I'm gonna change it and then put it here. Okay, so methyl now is there. And I will have hydrogen here. And of course, I can have the methyl group. I can have it on the left side as well. Okay, so let's copy paste this one, put it there. And we're going to erase this hydrogen. Okay, put the hydrogen on the right side and the methyl on the left side. Okay, now the dihedral angle between those 2 methyl groups is going to be 60. And the same thing here, the dihedral angle is going to be 60 degrees. Okay, these 2 conformations, they have a name, and the name for them is gauge. Okay, so in gauge, dihedral angle is around 60. Okay, because the dihedral angle is smaller than 180, that's going to make the system unhappy, and it will create technically repulsion. Okay, so you're going to get repulsion, and how much repulsion we get? It's going to make the system unstable by 3.8 kilojoule. Okay, so the interaction between 2 methyl groups. The interaction between 2 methyl groups in an anti position, okay, sorry, in a gauge position, when theta is 60 degrees, it will cost you 3.8 kilojoule. Okay, so keep this one in your mind. Now, you have 2 gauge conformations. In one, methyl is on the right side. The second one, methyl is on the left side. Of course, you have one staying on the top. Okay, and how about the gauge position? The gauge position, okay, sorry, the eclipse position. Eclipse position. You can have eclipse. Let me erase those. Okay, we can have couple of eclipse positions. Okay, let me show them. Okay, the first one is when we have hydrogen. Okay, hydrogen is facing a methyl group. Okay, then I have, for example, CH3 here, and then H. That's one. I can have CH3 here, and hydrogen there, and on the top also I can have hydrogen. Okay, and last one, I can have CH3 facing CH3, and hydrogens are facing hydrogens. Okay, let's talk about their energies. Okay, again, based on this diagram that I presented at the beginning, HH is 4 kilojoule, HCH 6, and methyl it will be 11. Okay, so keep this one in your mind. And now let's go after energies. These two, they will cost us 4 kilojoule. Here, 6 kilojoule, and this one it will be 6 kilojoule. So 12 plus 6, that's going to cost us 16 kilojoule. Okay. Again, here I go 6 kilojoule, 4 kilojoule, and that one 6 kilojoule. I got 16 kilojoule. Okay, 16 kilojoule. And what's the difference between them? The difference between them here. Okay, look to those methyl hydrogen. Now they are on the left side. Okay, everything looks the same except position of the HCH3 from right went left. So I will get two eclipse positions. They have exactly the same energy. The only difference between them, position of the methyl group from right, it will go to the left side. And how about here? This one is going to cost us 4 kilojoule. That one also 4 kilojoule. How about this two? That one is going to cost 11 kilojoule. This is new one. We did not have it before. So I got 11 plus 4 plus 4. That's going to cost 19 kilojoule. This is going to be the most unstable, okay, the most unstable, conformation. So technically, you're going to get a barrier, and then you'll get a bigger barrier, and then you get the same barrier, and you go down. So one of the barrier is going to be bigger than two neighbor barriers. So I expect it to be like that. Okay, let's present that one. Okay, this is the diagram of butane. Okay, as I mentioned at the beginning, you have anti-position. Okay, when you go through eclipse position, you will get 16 kilojoule. Why? Because the methyl groups are not facing to each other. Okay, the methyls are there. Okay, they are not facing to each other. Methyls are facing hydrogen, and that's going to increase the energy of the system by 16. Again, you get 4 here, 6 there, and 6 here. That's totally is going to be 16 kilojoule. Okay, now you rotate. When you rotate it, you get new condition, and this condition, the two methyl groups are 60 degrees far from each other, and we call it gauge position. I want you to be sensitive to energy of the starting point. This is energy of the starting point, and compare it with energy of this conformation that we got. Okay, and that one, okay, the energy here is up by 3.8 kilojoule. Okay, why? Because in any gauge position, okay, yes, it's a staggered position, but the gauge position, you have two methyl groups that they are 60 degrees far from each other. They used to be 180, now 60 degrees. Because they are 60 degrees, they will be too close to each other. They will repel each other, and they will make the system unhappy. And that's the reason energy here, energy went up. How much? By this amount, 3.6 kilojoule. So the reason that the new structure that we got, it has 3.8 kilojoule higher energy than the starting point, is because of the gauge condition. Okay, you're going to get another gauge structure, and this is going to be another gauge structure, and the gap here again is going to be 3.8. Remember, I said we can have two gauge structure. Methyl group used to be on the right, now is on the left. Okay, and but in order to get the second gauge structure, we're going to have two methyls that they are facing to each other. Okay, so those two methyl groups are going to be facing to each other, and it's going to decrease the energy of the system by 11 kilojoule. Well, here you have 4, and that one also 4, and that's totally is going to be 19 kilojoule. Okay, and this is the answer for that 19 kilojoule barrier. Okay, now if you rotate that one, very soon you will get another gauge structure, and if we keep rotating it, we get eclipse structure that has methyl facing to hydrogen, another methyl facing to another hydrogen, and so each one is going to cost you 6 kilojoule. Okay, 6 here, and that is 4. So 6 plus 4 plus 6, that's going to be 16 kilojoule. Okay, so expect this barrier to be 16 kilojoule, which is the same as the starting one. Okay, I should continue this one until here. Okay, That one is going to be 16 kilojoule. Okay. And so we got two gouge structure conformations. Okay. And the angle between them is around 60 degree, and because it's a 60 degree, it's going to make the system unhappy. So you're going to get repulsion. And again, this is the reason for having, like a 3.8 kilojoule energy, because the two methyl groups are going to be too close to each other. The system will be unhappy, and the energy is going to raise. Okay, so back to strengths that we talked about them. Whenever you have two hydrogens facing to each other, the system will be unstable by 4 kilojoule. And if you replace the hydrogen by a bulky group like methyl, it will go up by 6. If you have two methyls facing to each other, it will go up by 11. And if you have two methyl in a gouge position, this time a gouge position, so we will have just a steric effect. Theta is 60. Well, all the previous ones, theta was 0. That means they were in eclipse condition. Okay, last one, they are not in eclipse condition, in a gouge condition, and the system, it will be unstable by 3.8 kilojoule. Okay, so I covered all the type of strain that we are dealing with. And the next lecture, I will be talking about the structure of cyclohexane, and we will present different conformation of cyclohexane. And I will see you very soon. Thank you very much.